Okay. Okay, so let's see. Okay, let's see. Last class, we explained procedure call, a leaf procedure, stack structure in RISC architecture. Today we're going to go to non-leaf procedures and see if the procedure can call another procedure. Before explaining non-leaf procedure, we need to see some calling convention. Calling conventions. Calling conventions are some rules that if you want to write assembly code to implement procedure call, you need to consider that. In this case, when one function calls another, some registers must keep their values, some registers are allowed to change. And these preserve and not preserve coming from that. Preserve registers are the registers that must have the same value after a function call. So these registers are mostly save registers. We also call them S0 to S11. We have a stack pointer, frame pointer, return address, and these information are always in top of a stack pointer, because when you put them in a stack pointer is always in here. So this is called preserved. Non-preserved are the type of registers that callee can change them without problem. Doesn't need to be worried about that. These registers are temporary registers. That's sometimes we call them T0 to I think 7, and also argument registers A0 to A9, 10. So we need to consider these two types of registers. Let's do one example. Imagine we have two functions, caller called foo and callee called bar. So the foo called bar, and when the bar done is go back control to foo. Okay, so this called callee, this called caller. I'm asking while executing inside foo, so the foo is getting start working, and which registers foo need to be worried about before calling bar. So normally we don't need to be worried about save registers, because save registers, if bar change them, need to return them back. So we just need to be worried about temporary and arguments registers. So the D is the best answer for that. However, the point is caller and callee need to follow conventions. If they don't follow conventions, everything gonna get problem, okay? Okay, yes, let's see which registers we can use in caller and callee. So for caller, normally caller need to be worried just about temporary register and arguments. We call them caller saved registers, and then do jump. When we do jumping, automatically return address is also gonna get updated with program counter +1. But what about callee? Callee has two parts: setup part and return part. Okay, for setup part, callee always get allocate memory, allocate the stack. So whatever was the stack pointer, we get new memory and change the stack pointer. Like for example, we can get 16, for example. In this case, if the stack pointer was that, when we get 16, the stack pointer is gonna come here, the new stack pointer, -16. Just need to add a stack pointer and a stack pointer and -16, because the stack is the backward when we want to put something, or when we want to push something inside. We are changing a stack pointer. We decrement a stack pointer to the number of bytes, because 16 bytes means 2 double word. Okay, so this is called stack allocation or memory allocation. When we did that, the only things that we need to be worried about is to actually save callee save registers. Callee save registers are save registers, return address, and callee need to preserve all of these callee save registers, and then do return. But before doing return, we need to do our job. So callee need to do some stuff, for example, computing something and put the result in arguments registers, put the result. We put the return values in this, and then restore whatever we saved. We store here, we load them back. Whatever we stored in the stack, we return them back, load. If, for example, we store S0 in offset, we load from the stack pointer, from the stack to the register. And also we load return address. After that, we deallocate the stack. We deallocate the stack means we change the stack pointer from here to go back to a stack pointer. We got 16 byte, we release 16 bytes. So here is 16, but this time is positive. And then we do jump and link return. Jump and link return format is like that. The return address that we took from a stack, we jump from there. So this is same as this. And we also put in X0 program counter +4, because this is jump and link again, but return. A jump and link return is a dynamic jump. You can put something in return address and jump there, that's very interesting. And X0 is always 0, so this is not changing that. Okay, so this is another example for registers. Let's see when this is all registers in a RISC-V ISA, instruction set architecture. So we want to see, this is a number of registers, 32 registers. A usage, we wrote the usage here. For example, X1 is return address. This is the convention name, conventional name for registers. Stack pointer is the X2. You don't need to remember these X's. If you use conventional names, it's better actually. It's easier and more understandable. So I'm asking which registers preserved on call. Which registers preserve on call means the callee must preserve it. X0, it is always 0. No one can. So preserved so all the preserved registers need to get preserved. Preserved registers are this X0 is always 0, so this is not applicable. Not applicable. A static pointer, yes. Global pointer, yes. We don't use global pointer, it's pointing static area, static registers, static memory. Thread pointer, we don't work with that as well. Temporaries, so we need to save these. They are special registers that we need to save them. They are preserved registers. But temporary, no, we don't need to save them. Save part, yes. Arguments, no. Save, yes. Temporary, no. So just 3 no exists here. Let's clean this up. As you can see, we don't need to be worried about temporaries and arguments. That's it. But we need to worry about, however, the X0 is always 0 with change. Okay, so now it's ready to go for non-leaf register. What non-leaf register means? Non-leaf register is a callee that is also caller. So it means not just somebody else call it, but that can call another one too. Why is non-leaf? It means in a tree structure, we have some leaf. So this is leaf, this is leaf, and the rest are non-leaf. Okay, so we are talking about these procedures. Let's see what's happening to them. In this case, these procedures called another procedure. Why we need to be worried about those? Based off convention, these actually non-leaf procedures need to save not just callee save registers, but also caller save registers, need to act both of them. So what must be saved before making the call? So this is the caller, this is the callee, but this is non-leaf, but this is callee but non-leaf too. And this is call another one that is also callee, for example 2, and this is callee 1, but this is leaf. Okay, so we call another one, this is gonna come back here, do a little rest, and this is gonna come back here and do a little rest. So the structure is like this. So we have one caller, 2 callees. The first one is non-leaf, the other one is leaf. Okay, so let's see what we need to preserve in each one. Okay, when a procedure calls another one, it must save on a stack in 2 different modes. First mode is a caller mode, the other one is callee mode. I forgot here. Right. Okay, so we are dealing with these parts. We have a non-leaf callee. So when we call that, this is call it, so we need to save S0 to S11 save registers and stack pointer. This is for mode of callee, and for caller we need to save temporary registers. We need to save temporary registers like T0 to T8, T7, sorry, and also argument register A0 to A9, for example, and return address. So we need to save all of these things. And when we come back, after coming back, what we need to do, we need to restore, so restore all of them. So we need to save them and restore stack for all of them that we saved, and also need to continue execution whatever else we were doing, and then jump and link return x0 and 0x1. This is convention. We always use like that. This is convention. Okay, so this is what happening in non-leaf procedure. Let's do this example in a C a code that is a recursive code. This is a non-leaf procedure, recursive code. What we are doing, factorial. So factorial, for example, 2 is equal to 2 multiplied by 1 multiplied by 1. So this is actually factorial of 0, factorial of 0, factorial of 1 is factorial of 2. Because factorial of 0 is 1, we need to consider factorial of 0 is 1. So actually factorial of 2 is just 2 multiplied by 1, but factorial of 0 is also 1. The code that we need to write need to cover this part. So let's see if this is following that. Imagine we are calling the main function, calling factorial main function called out is equal to fact0. So let's see what is out here. So we are jumping here, n is 0. If n is less than 1, return 1. So the out is 1, so it's correct. Perfect. So we need to implement this one. What about something bigger, like 2? If it's 2, we are jumping here, so n is 2. Okay, going here in a first for factorial 2, n is 2, n become 1, and if n is less than 1, is not, so we return actually 2 multiply fact 1 n minus 1, so is 1. So again we call fact 1, fact 1. So we jump fact 1, n is 1, n is 1. Is less than 1? No. So we return 1 multiply factorial 0. So we call factorial 0. So We should maybe put here return 2 multiply fact 1 instead of that to make it more understandable. So n here is 0. When n is 0, we jump there. If it is less than 1, yes, it is less than 1. So we return 1. So return 1. So we don't call anything else. So we go back here. We put 1 here, and then return 1 multiplied by 1. Return back here, 1 multiplied by 1, and return 2 multiply this. So we return that. So it's going to be 2 multiply 1 multiply 1. So is equal to 2. So out is equal to 2. It is correct. So this is how recursive function works. So let's see how we can implement this using actually assembly language. So first of all, why this is non-leaf? Because each function, for example, n, call another function fact n, it's called another function fact n minus 1, and that call another function fact n minus 2, and so forth. So that's why this is a nested calling. So therefore it must save two things. It needs to save return address and also n, because we also need to save n to multiply that together. So we need to save that as well. Okay, how we can do that? We can use a stack. We can use stack for n and return address. So that's what we need to do for implementing this. So the key idea is any function that calls another function must protect return address. That's normal. Okay, that's the code. Here I'm just asking. I want to explain it just like that and explain the stack. I think for your assignment, you also need to see what's happening inside the stack when call and return happening. Okay, so to understand that, let's see how this works. Okay, so before tracing this and explain this, I actually change that recursive function in another way. What about if we write a factorial function n like that? We say, okay, if n is less than 1, go to base is for 1. Other than that, n is n minus 1, and then call fact n, call itself, and then put what else? Oh, put n is n multiply fact n, okay, and go to done, and in base, okay, so doesn't need this. Okay, this is for fact, this is for base. Base is n is 1, okay, and done is return n. Okay, this is very similar to assembly, but still is high level. So is what because in assembly we need to do two things. we need to do if and else. At the same time, if and else, and recursion. So we need to consider both of them. To do if and else in RISC-V, we need to do this thing. We need to have a base one. And oh, I forgot something. We have a jump here. We have a jump, down. Oh yeah, I wrote that. Go to down. That's correct. Yeah, that's fine. Okay, so this is how we are dealing with if and else and recursive at the same time. Okay, now that we know this high-level representation, let's go to the low-level representation. Okay, this is exactly similar to the C version, okay, but a little bit similar to RISC-V as well, okay. So let's see what's happening here. So first of all, factorial is a non-leaf. So when we call it, the first things that the non-leaf procedure need to do is to get allocate data. Allocate and store into stack. What we store in the stack, two things that we want to save. One is n, and another one is return address. Return address, or a return address. So a return address is always in x1. And we also use x10 for n. So we use x10 for n, okay? So, sorry. We're going to explain this and then go for the stack, what's happening in the stack. Okay, that's allocating. Then we are doing the process that we need to do here. What we need to do, we need to decrease n by 1. We put in x5 1, and we put in x5 1, and we check if n is less than 1. So if n is less than x5, x5 is always 1. So if n is less than 1, we go to the base. Exactly what's happening here. Other than that, we decrease n. We are here, decrease n. And then we call function again. Because we call function again, we are actually kind of calling factorial n minus 1. Okay? And we call that here. And what else we need to do? We use x6 to save the multiplication. N multiply fact n is going to x6. It's just a temporary register to save that. We are allowed to use that without worrying about anything. So we use x6 and multiply x6. x6 actually is this oh, sorry, this is not x6. x6 is actually the factorial from before. We took it from stack, so it's factorial n minus 1. And we multiply it by n and put it in x10 as a return value. Return value. And x10 is the argument register. Okay, we put that there, and then we go to down, because base is just for case that n is 0. Okay, we go to the down, So what happening in done here, but because is again a non-leaf procedure, we need to do convention. What is the convention? We actually deallocate a stack. So we deallocate the stack and restore return addresses. Restore. We do restore and deallocate, and we are ready to return. How we return? Return x1. We already have x1. We took it from stack, so we are jumping there or return from there. Okay, that's good. So that was just but I'm not gonna ask something like that to explain. Most of the time I'm gonna ask inside the stack, what happening inside the stack. So also in your assignment, I think we had something like that, and I asked you, that was for Fibonacci. You need to see what happening inside the stack. Let's do this for see what's happening inside the stack in this example. Let's clean this up. Okay, imagine we have a main function, that this main function actually calling load immediate x10 2. So we want to find Fibonacci, factorial of 2, for example. Want to compute this, and then we are calling jump and link x1 factorial. So this is like a main function. It's like a main function in C. So imagine we have something like that. Let's see what's happening inside the stack. We didn't touch a stack yet, so whatever was a stack pointer still is there. That's a stack. Okay. So we also have register x1 or return address, and x10, that is actually n. So n right now is 2. Return address is so for return address, imagine this is the main function, and return address main, when we jump to factorial fac2, this is return address main. When here we call factor 1, this return address we call that return address RA2 for factorial 2, and here we call that return address 1 for factorial 1, and this called another one for fac0, and fac0 doesn't need anything because this is a leaf, and this has a return to factorial 1 using this, and this also use RA2, jump to this, and this use RAM just to come back to main. Okay, so we need these addresses. We need these addresses, these return addresses. Okay, we just need these return addresses to get saved there in the stack. Okay, let's see what's happening in the stack now. Okay, we call fac2. We go here, fac2. So we allocate a register, a stack pointer moving to here. That's good. We put n, that is x10, inside here. We put 2 here, and we put return address in here. Return address here is return a main, RAM, return address main. We don't know what is that. Whatever is that, we call it that. We save it. We store it in the stack. Now we keep going. We are checking. We put x5 is 1. That's okay. N is 2. Is it 2 less than 1? No. So we don't jump to the base. So we decrease it. N becomes n was 2, n becomes minus 1, 1, n becomes 1. And then, return address here is RAM. Good? Okay. So we have that. Who put this return address? The function jump and link put that. Remember? Okay, good. So now what we need to do, we need to call again jump and link. When we do jump and link, this gonna get changed. This value gonna change. Is gonna be return address 2. Right now we are here. So we call that again. Control coming here again. It get another 16-bit stack pointer moving here, stack pointer coming here. It put n x10, that is 1 here, and return address, that is return address 2. Okay, perfect. Go here, we put x5 1 again. Is that less than 1? No, because it's 1. So make it decrease it, so it becomes 0. Okay, becomes 0, and then call factorial again. Okay, we call factorial again, but this time factorial n is 0. Okay, we call that again. When we come back again in a factorial, again we allocate memory. We change the stack pointer here. This is not the stack pointer anymore, and put n here. N is 0, and put return address. Return address is return address 1. Okay, and that's good. We come and put x2 is 1. It's correct. Is n was 0 less than 0? Yes. In this case, we jump to base. We jump to base. Okay, we jump to base, and what's happening? We put in x10. We put in x10 the value of 1. This is not 0 anymore. It's 1. Perfect. And then after finishing that, where we go? We go the next. The next is this. So we do the, because when we call the base, we keep doing the rest. We don't care. The label, so we are here. What we are doing, we are loading x1. We are loading whatever was in return address. A stack pointer. We are checking x2 is a stack pointer. We didn't save a stack pointer. We don't need that because the stack pointer is going to change by itself. Anytime that you are actually pushing and popping, a stack pointer is changing by itself. Okay, it's not doing by itself. Actually, you are doing here like with pushing and popping. Okay, so let's see what's happening. So what you are doing, you read return address from here. Stack pointer is here. A return address 1. You put return address 1 in x1 and deallocate a stack pointer. A stack pointer move to here again. We took return address. And another thing that we do, and we jump to return address 2. So it means we are jumping to here, because here is return address 1. Okay, remember? We are jumping here. We are right now here. Okay, and the stack pointer is moving up. When we are doing jump and return, we are coming back. Let's clean this up. Change the color. We are going back instruction after jump and link. We are doing here. What is in the stack pointer? The stack pointer is right now here. A stack pointer x2, 1 is here. Okay, we put 1 in x6. Okay, we have x6 here. We put it 1 here. Good. This 1 is actually p of n minus 1. Sorry, Fibonacci n minus 1. Factorial n minus 1. Okay, so we put 1 here and go to next instruction is, we did load. We multiply that with x0, x5, x10, sorry, x10 was 1. So it's kind of multiplying this with this 1, multiply 1, put it in x10. So x10 is still 1, okay? And then jump to down. Jump to down. When we jump to down, so we have these values here. We restore return address. So return address from x. We didn't change here actually. It was return 1 right now, but right now it becomes 2. We forgot to update that last time. It becomes return address 2 now. With this, so it's return address 2. After reading from stack, we pop a stack, deallocate it. So it means from here we move a stack pointer to here, okay, and jump to return address 2. Jump to return address 2. So we were here, jump to return address 2, rest of factorial 2. That's interesting, okay? So what else we need to do? When we jump here, again, let's change the color. We are in, like for example here, okay? We are in fact 2 now. Okay, so what's happening? We take a stack pointer. The stack pointer is x2. Whatever is there, 2 is there. We read that, put that in x6. What is okay? We multiply x6 by x10. So we multiply 2 and x10. That is 1. And put that in another extent. So the new extent gonna be 2. Gonna be 2. That's good. And we jump to down. We jump to down. So these registers are these values. X6 has 2, X10 has 2, and return address is return address 2. Perfect. Let's see. Did we update return address? Yes. We also need to update return address. We didn't. This is when this happening. we take the return address, that is return address M, with this. So here is return address M now, main return address. Perfect. Okay, so we jump back again, and this we jump back again. Let's do another color to can explain it more clear. Maybe choose red again. We jump back here. Actually here. Here, okay. We jump back here. We load x2 0 that wait a second. That is 2. We took 2 and put it in x6. I think we did this 2 times. Anyway, I think we did that 2 times. Okay. Oh yeah, sorry. This is when this is happening. We jump here. We jump here, not RMM is here. So we jump here, and the factorial is the x10 is the output, and x10 is 2 multiply 1, that is 2 factorial. Okay, so at the end it becomes a little confused, but I think you understand what's going on here. We are putting a stack, and we are pushing a stack and popping a stack, and whatever was inside the stack, we return it after jump and multiplication, and this is what's happening in a recursive form. Okay, so next class we're gonna talk more about actually ASCII characters, and we finish actually assembly code, and we're gonna go to designing the different part of CPU. You know, we're gonna move from instruction set architecture to like a data path design, data path, and also controller design. Okay. So for assignment, you can use this idea as well. Have a good day.